Hi guys, welcome back to another video of me teaching, and today I have this question on the board for you guys. So why don't we just get into the question? Well, here we want to prove f of n is equal to this big thing is an integer. Well, the first thing you notice is that we have cosine square of something, but we don't like cosine square. We like cosine power of 1. So we are going to try to reduce the power. And we can do that by using the double angle formula. So we know that cosine of 2 theta is just equal to 2 cosine squared of theta minus 1. And then if we move this here and divide it by 2, then we know that cosine square of theta is just equal to 1/2 times 1 plus cosine of 2 theta. This is also an identity. So if we plug this into there, then we get pi k goes from 1 to n of 1 plus 4 times 1 over 2 is just 2, multiplied by 1 plus cosine of 2 times that. So 2k pi over 2n plus 1. And now we can unpack this. So you get capital pi k goes from 1 to n of 1 plus 2 is just 3, and plus 2 times that. Okay, so now I'm just going to see that if we have 2 cosine of theta, and what reminds you of 2 cosine of theta? Well, the sum of 2 complex conjugates. But before we get to those, I'm first going to let theta, this is going to be a new angle, to be 2 pi over 2n plus 1. Now, this is basically the base case for this. Okay? So, doesn't this look a lot like root of unity? Yes. But that is going to be a bit later. So now we can go back to seeing that 2 cosine of theta is just the sum of 2 complex conjugates. So can't we just let z to be e to the power of I theta? Now this is just another way to write the complex number. And we know that z conjugate is actually just e to the negative I theta. So now what do we do? Well, don't we need to take z to the power of k? Because then this is just I times this. But the angle is 2k pi. So you need to first raise z to the power of k and z conjugate to the power of k. So you know that zk is e to the I k theta. Z conjugate, since the modulus of z is 1, is just 1 over z to the power of k, z to the negative k, is equal to e to the negative I k theta. And now we can write these out. E to the I, 2k pi, 2n plus 1, e to the negative I, 2k pi, 2n plus 1. So now we know if we add these two up, then it will just be 2 times cosine of this. So this will just be capital pi, k goes from 1 to n, of 3 plus this, like I said, it will just be this plus that. Now, this kind of reminds us of when we're doing second order differential equations, don't we have to change this differential equation and map it into its characteristic equation? Well, that is actually what we're going to do here. But to make a characteristic equation, usually they're all quadratics, right? But here, it's not a quadratic, but that is actually an easy fix. We can just take out z to the power of negative k. So it will become z to the power of k, so z to the power of negative k, and the inside is just, do it in order, this first, so z to the power of 2k, plus, then this, 3 times z to the k, then of course, plus 1. So now, this quadratic's characteristic equation is just, we can replace z to the power of k with x. So it'll just become x squared plus 3x plus 1 equals 0. Now, if we assume that there are two roots, alpha and beta, then you notice that this was actually what we did in the previous video. So in the previous video, we found out that alpha to the power of n plus beta to the power of n is an integer. And that is going to be a very useful information for us. So now I'm going to use Vieta's formula and figure out alpha plus beta and alpha times beta. So we can see that alpha plus beta is, use Vieta's formula, will be negative 3, and alpha times beta will be 1. And this means that beta will be 1 over alpha. This is also very important information. Okay, so if we change x back into z to the power of k, then we know that this quadratic has two roots, alpha and beta. So if a quadratic has two roots, alpha and beta, then we know we can always factorize it as the variable minus alpha times the variable minus beta. And in this case, the variable is just z to the power of k. So you can factorize this to make it equal to, of this we keep, but it becomes z to the power of k minus alpha times z to the power of k minus beta. Okay, so now I'm going to rewrite beta as 1 over alpha. And then I'm going to do a little trick. I'm just going to multiply z to the negative k into this bracket. So this will be, the first bracket we have to keep, but then the second bracket will be, that times that is just 1, and the minus 1 over alpha is just alpha to the negative 1, and then this is just z to the power of negative k. And now, the second thing I'll do is that I'll factor out a alpha to the negative 1 to the outside. So it'll just be capital Pi of alpha to the negative 1, then multiply by, as it is. And then, remember that we took alpha to the negative 1 out of this one. So then, this 1 becomes an alpha, minus, this is gone, so minus z to the power of negative k. Now, you might be able to notice what I'm trying to do. I'm trying to make alpha to be the variable and z to the power of k to be the root. Now, what do? Well, we just need this to swap, right? But that's really easy to do. We can just put a negative outside. So, it'll just be of, the first bracket will be alpha minus z to the power of k, and alpha minus z to the power of negative k. But now the problem is, this is z to the power of k, and this is z to the power of negative k. But we want this to also be z to the power of k. So, if I rewrite z, so we know that z is just, so we know that z is equal to this. So this is actually the base root of unity. So this is when k is just equal to 1. Now, since this is 2 pi over 2n plus 1, then we know that this is the base root of alpha to the 2n plus 1 is equal to 1. And now, we can actually draw that out to make it very clear. So, we can just draw a circle. So, this is one root down, and we know that there are an altogether of 2n plus 1. So we know that, excluding this one, there are 2n altogether. So then that must mean that there are n on the top half and n on the bottom half. For example, you could do a drawing like this. Okay, so we know that z to the power of k is on the top half. But before we get to that, I'm first going to explain what k can be. So there are actually two ranges of what k can be. The first range is when k starts from 0 and ranges up to 2n. And the second way is when k starts from 1 and ranges up to 2n plus 1. But in our case, our capital pi starts from 1. So we are going to focus on this one. Okay, so back to where I said. No, z to the power of k is just on the top half. And we know that the values of k on the top half is just ranging from 0 to n, right? And we know that z to the power of negative k is on the bottom half. So this is z to the power of k, and this bottom half is z to the power of negative k. And now, since z to the power of k ranges from 1 to n, then we know that z to the power of negative k must range from n plus 1 to 2n. So now that we know this, we can see that z to the power of negative k is actually the same as z to the power of k on the condition that k ranges from n plus 1 all the way to 2n. This is very, very, very important information. Because now, the first thing I'm going to do is I'm going to take out this negative alpha to negative 1 to the very outside, even outside of the pi. And then I'm going to separate this pi into two separate ones. So this is equal to, if we take this out, then of course we have to raise this to the power of n because we're multiplying it n times. So negative alpha negative 1 to the power of n. Then the first pi stays the same, ranging from 1 to n of this. But then the second pi goes from n plus 1 to 2n. And now z to the power of negative k goes to z to the power of k. And now, using the pi theorem, we can put these together into one big pi ranging from 1 to 2n. So we can change this back into still negative alpha negative 1 to the power of n. Change this into one big pi where k goes from 1 to 2n of alpha minus z to the power of k. Okay, so now if we just expand this pi out, it will just become alpha minus z times alpha minus z squared all the way to alpha minus z to the power of 2n. Now, this by itself isn't significant, but if we multiply an alpha minus 1 and of course divide it by an alpha minus 1, then look, this is just a root to alpha to the power of 2n plus 1 minus 1 equals 0. It's a root to this equation. So by definition, we know that this factorization is equivalent to this. And now we can factorize this a different way using the traditional way, and we can factorize it like this because we know that the power is odd. So this is equal to, we can factorize it as alpha minus 1, and then if you do this in your head, you see that it will just be alpha to the 2n plus alpha to the 2n minus 1 all the way until 1. And the bottom is just alpha minus 1. And look, cancel, cancel. So we can now get rid of the pi and make it into negative alpha negative 1 to the n times that. Alpha 2n plus alpha 2n minus 1 all the way until 1. Okay, so if we expand this, then we see that it will just be negative 1 to the power of n. We'll ignore that for now, but then we'll multiply in the negative alpha, then we'll multiply in the alpha to the power of negative n. So this will just be negative 1 to the power of n, leave it outside, multiply by this. We have to multiply every single term by alpha to the negative n. So it will just become alpha to the n plus alpha n minus 1 all the way to alpha to the negative n. And now we can use this information. Beta is equal to 1 over alpha, or beta is equal to alpha to the negative 1. So this is just equal to negative 1 to the n multiplied by alpha n plus alpha n minus 1 plus all the way. I'll just write one more term plus beta to the n minus 1 plus beta to the n. And now we can start pairing because alpha to the n plus beta to the n is an integer. So we can start pairing. This can go with that, this can go with that, and we keep going. So this is equal to negative 1 to the n multiplied by an integer. And of course, this is easily an integer, so you know that the whole thing has to be an integer. So we have proved this very fascinating question. So thank you guys so much for watching, and if you enjoyed my video and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.